today for. Um, we talked about errors, or rather, did errors. One of those things. Um, anyhow, what are errors? Errors are natural variations in data due to the measuring device. Different measuring devices can produce different results, or even the same measuring device can produce different results. More likely, your error kind of show you how reliable your data is. Um, in our case, we would say roughly that 68% of the data should lie within the two error ranges, the higher and lower value above and below the mean. Um, and you kind of see that when they talk about polls and statistics, and they'll talk about, well, this candidate is supposed to get 50% of the vote with a confidence interval of 2.5%. That would mean that they can get as high as 52.5% or as low as 47.5%, and they have 95% confidence it's going to fall within that region, otherwise known as 2 sigma, 2 standard deviations. Um, a really kind of good example of this, of just the variations and due to maybe your measuring equipment, is two different types of experiments. I call it the neutron problem, but basically a neutron outside of the nucleus is not very stable. When you pull a neutron out of a nucleus, it will decay in roughly 600 seconds. And it's called beta decay. It decays into a proton, an electron, and an electron neutrino. Um, Inside the proton, incredibly stable. Inside the nucleus, it's incredibly stable, but outside it is not. And so they try to measure the actual decay, how long it's actually going to stay as a neutron before it decays into a proton. And there are two different types of experiments they use. One is a beam of experiments where basically they have a huge beam, a neutron density beam, and based off its density, they kind of estimate how many neutrons are there, and they send them into a magnetic or electrical field, and they count how long that they last over a certain period of time. The other one is a bottle experiment where basically it's just ultra cold, and they know how many they start with, and they count how many are left after a certain period of time. The problem is that they're off. I don't know the numbers off the top of my head, but let's say the beam experiment is like 588 plus or minus like 2 seconds, and then the bottle experiment is like 596 plus or minus, I don't know, 1.5 seconds. The major problem is that this can go as low, and this is actually known as 5 sigma, meaning 5 standard deviations, so like 99.9 something percent confidence that it's going to fall within these regions. Both experiments are really reliable, but notice that their errors don't overlap, because this is going to be as low as 594.5, and this one could be as high as 590, so they do not overlap. They're both sound experiments, and the reality is they don't know why that they're not even in close to overlapping. They should, but they don't. And so there could be something at some sort of new physics we don't understand, that's causing this problem, or maybe there is a problem with the experiments and they've just not realized it yet. But those error bars are what's telling us that there's something majorly wrong. If they overlap, they could probably say, okay, yeah, that makes sense. That happens sometimes. Um, but in this case, they're not overlapping, so that's kind of a problem. So they're trying to figure that out. I haven't figured it out as far as I know yet. Um, so mistakes and errors. The two probable reasons for variation in measurement are mistakes and errors. Mistakes: a group could have measured the wrong object. That doesn't happen too often. Used the wrong procedure. Yeah, I've seen that before. Read the measuring instrument wrong. This is very popular. Popular by meaning that it happens a lot. Basically, people think they read 2.4 grams, and it was really 2.04 grams, and they'll write that down wrong sometimes. Another one that's really common is mistakes in calculations. We're not human computers, and even when we use computers, i.e., calculators, we still screw it up. Now, the reasons for the errors: there's a slight variation in equipment. Each of your triple beam balances is probably not going to produce the exact same result on all uh, items, and I know that. Limited degrees of precision with equipment. This is like measuring, I don't know, what's really small. Let's take a bed bug. Measuring a bed bug with a ruler. Bed bugs are incredibly small. You really can't measure it with a ruler. There may be, I think, a millimeter at best, but you're not really going to get a good, accurate reading because, I mean, it could be 1 millimeter plus or minus 1 millimeter. That's when your error is the size of the actual object, it doesn't really make a lot of sense. Reasons for error? Oh, I'm still learning on this. Environmental conditions. Not too much of an issue here, but if you're in the field, that could be an issue. Like geology classes, if I remember correctly, we had to mass things out in the field in geology. The wind could kind of make a difference. And then human factor. Yeah. So we use maximum deviation. Turn this off because people don't shut up. Maximum deviation in this class, we utilize it because number one, statistics is not required for the class, so can't do that there. Another thing is you can maybe actually do errors with lower level classes, at least to some degree with this, without them, finding the variances and finding the standard deviations and whatnot. So that's kind of the idea of why we do this. And it really comes actually pretty close as long as you have enough data points to a traditional statistical method. So I'll do an example and kind of walk through it. But let's say Nancy near normals measures a pi to be 3.3, 3.2, 3.4, 4.2, etc., etc., etc. What first thing you do is you find any outliers. Not necessarily statistically sound to get rid of outliers, but in our case we will. And clearly the outlier, found my cursor, is right here, 4.2. I don't really know how you measure a pi to be that big, but it was that big. And the rest of them, the only one that comes close is 3.5, and that's pretty far away. So that one's clearly an outlier. You generally want 8 data points. Doesn't always going to be the case, especially if we have like a really small class like we do. But you do want 8 data points, just because it helps in approximating the actual error. You're going to find the average, and you're going to find the second smallest, or as will learn today, first of its density, and find the difference from the average, and then find the second largest, or first of its density, and then the difference from the average. Use the larger of the two as an error, and we record it as plus or minus error, the unit. So we will record this as mu, which is your mean. That's a Greek letter, in case you didn't know, mu, plus or minus sigma, and that is your error, otherwise known as standard deviation, and that is a Greek letter, sigma. It's usually going to be the smallest marking of measuring devices, and we're going to use our 0.1 grams per mass and 1 milliliter per volume. So, because those are the smallest measurings that we can have based off the devices that we're using. So I'm going to work through this specific example. First, I need to find my average, and so I will do that. There's 3.3 plus 3.2 plus 3.4. There are 3 3.5s, I noticed, so I'll just put 3 times 3.5 plus, let's see here, 3.4 and 3.3. And I'm going to put kilograms because I'm supposed to put units on it, so I'll put it outside so it gets everybody. And then divide that by 1, I think it's 8. 1, 2, 3, 4, 5, 6, 7, 8. 8. Alright, got my calculator because, calculator. So 3.3 plus 3.2 plus 3.4 plus 3 times 3.5 plus 3.4 plus 3.3. Divide that by 8. That gives me I'll say 3.9. So that is our mean. Alright, well, we're going to do the second largest. We could use repeated values. I kind of didn't say that earlier, but we can. So 3.5, 3.5. So since there's two 3.5s, that's what we'll use. And so, oopsie. So that'll be 3.5 minus 3.39 is going to be 0.11. And then for small, looks like 3.2, 3.3, so 3.3, and that one's going to be 0.09. So the largest is 0.11, so we write this as 3.39 plus or minus 0.11 kilograms. So that means that for all the measurements, 68% of instances should occur between 3.5 and 3.28 kilograms. So we have about 68% confidence that it's going to be in that region of mass for the pie. Why pie? I don't know. Sounds good. Pot pie. Chicken pot pie. Oh god, that sounds really good. Error bars. So what an error bar is, let's just use this one. Let's say I were to graph mass versus volume. And let's say it's 1, 2, 3. So this is 1, this is 3, 4, and then I don't know what the volume is. We'll make it up. So if what I would do is 3.39 would, I don't know, let's occur right here. So for the error bars, I should have drawn this bigger, but basically I would say, okay, 0.11 above, 0.11 below, and then I draw a line through it, so that when you look at that data point, you know that it could range between those 2 points. Clearly not, because I'm also spanning like a whole 1 gram, but I think you get the picture. So that's what an error bar is. That's what you have to do today. And due to limitations of Google Sheets, which some students use, I think the other programs by now all allow you to do X and Y error bars, but because not all programs have quite caught up yet, we're only going to do Y error bars just for that reason alone, unless specified. And this kind of shows you what it kind of looks like. Most of the time your error bars are not going to be a constant value, but for our purposes we generally are going to call it a constant just because it makes things easier. And so yeah, like I said, the error bar kind of shows the uncertainty of your data, because you expect it to be, like for this one right here, the mean would have been 5, but you can go as high as 6 or 4. Based on, it's arbitrary units, but you get the picture. It can be kind of within that region. Alright, that is it for this lecture. I will see you tonight in class. Sorry I should have posted this earlier, but this is, I think, my 5th time trying this. Hopefully this time's going to work. I'm not used to doing this at home. That's for sure.